Hi everyone. Today we are going to discuss on two topics: multi-threading and real-time operating system in LabVIEW. First, we have to discuss on multi-threading in LabVIEW. Generally, multi-threading and real-time operating systems are fundamental concepts in embedded system and real-time computing. So how it is used in LabVIEW? Multi-threading is nothing but it has the ability of a CPU or a single core in a multi-core processor to provide multiple executions concurrently. So the threads are the smallest sequence of program instructions that can be managed independently by a scheduler. Here, the functions of multi-threading in LabVIEW. While integrating multi-threading and RTOS concepts in LabVIEW, it is more effective for developing complex and real-time systems. LabVIEW has the opportunity for the user to implement multi-threading and real-time models for the application development and run it on real-time operating systems. Now we are going to discuss how we can approach multi-threading and RTOS process in LabVIEW. First, multi-threading. So LabVIEW inherently supports multi-threading and parallelism due to its data programming model, which allows independent sections of code to run simultaneously. So the main key facts that enhances the multi threading concepts in LabVIEW is: first one is parallel execution, timed loops, reentrant VIs, queues, notifiers, semaphores, and occurrences execution systems. We will discuss one by one in detail. In parallel execution, LabVIEW automatically runs independent code segments in parallel if there are no data dependencies between them. So we can easily implement the parallel execution. So we can use timed loops to create tasks that need to execute at precise time intervals. So it will give control over execution, timing, and prioritizations. Then reentrant VIs. So it enables reentrancy for VIs to allow multiple instances of the same VI to run in parallel, each with its own memory space. Queues and notifiers. It uses queues for safe first in first out based inter-thread communications. So notifiers can be used for broadcast communication where one thread notifies multiple waiting threads. If you consider semaphores has the control access to shared resources and prevent race conditions. Occurrences are used to signal events between threads. Then execution system LabVIEW allow assigning different parts of code to specific execution systems. Examples: user interface, standard data acquisition to optimize performance and responsiveness. The next one is real time operating system in LabVIEW. Generally, the real time operating system is to perform a particular task in real time. So, LabVIEW real time modules enables the development of deterministic applications that run on real-time targets such as NI compact Rio, PXI controllers, or other real-time hardwares. So why we need to do RTOS in LabVIEW? The first one is deterministic execution. In if you say the deterministic execution, the LabVIEW ensures that tasks are executed within specified time constraints. So mainly it is for industrial applications. We have to perform the task within the specified intervals where we can make use of this RTOS, and suitable for applications that require reliable and repeatable performances. Then real-time targets. We can deploy the LabVIEW code to real-time targets, including compact Rio, PXI systems, and real-time enabled PCs. Then priority based scheduling. LabVIEWRTOS uses priority based primitive scheduling to ensure high priority tasks get CPU time. Configure task priorities to manage the execution order. And it acquires low level hardware access because it directly interfaces with hardware input output for precise control and data acquisition. Then embedded system. We can develop an application for embedded system where timing and flexibility and critical reliability everything is achievable. Network communication. The real-time applications can communicate with other systems over networks like TCP/IP, UDP, and other protocols. Here, how we can implement multi-threading as well as RTOS in LabVIEW. A step-by-step process. First, we have to develop parallel tasks. So we have to design our application by identifying independent tasks that can run in parallel. We can use LabVIEW's data flow model to naturally achieve parallel execution. Then creating timed loops. The timed loops create tasks that require precise timing. So we can set loop priorities using timing parameters. Then re-entrant VIs. The re-entrant VI is nothing but it allows multiple instances to execute concurrently without allowing the shared conflicts. The next one is inter-thread communication. We can use queues and notifiers as already we discussed in the previous slide of multi-threading. So the queues and notifiers for processing data between threads safely. We can implement semaphores for resource logging to prevent race conditions. Then we can deploy it real-time targets. We can configure our project to target a real-time device, and we can develop our applications of whatever we need, and we can implement with real-time hardware for execution. The next thing we have to do is real-time monitoring and debugging. So LabVIEW is mainly meant for real-time monitoring tools to observe the task execution, timing, system performance, throughputs, out everything we can monitor in real time. So also we can debug and optimize your real-time application to meet the performance requirements. And also it has the capability to perform synchronization, interrupt handling, as well as memory management. So because the RTOS offers synchronization primitives like semaphores and utexes to manage access to shared resources, so which will avoid the critical path for preventing race condition and ensures data integrity. The interrupt handling. So the RTOS handles interrupts with minimum latency and allowing high priority tasks to respond quickly. We have interrupt service routines which can signal tasks or process data using RTOS event mechanism. Also the memory management. The RTOS has the high capability to manage, allocate tasks and ensure efficient use of limited resources. So it has the capability to avoid allocate dynamic memory for real-time applications. So we can discuss with a small example like data acquisition and processing, because we have already discussed about the various steps in data acquisition as well as data processing. In data acquisition, what are the things we have to done? We are going to measure your physical parameters, and we have to collect the signals, and we are interfacing with PC through the DAC. Now we have to break down the tasks to run parallel. First thing, we have to acquire the data from sensors. The next task is we have to process the data and analyze it. The third one is we have to store the data and prepare the report. So in this way, we can break the huge tasks into a simplified tasks like uh, acquiring the data as a task and transferring the signal to the DAC is a task, from the DAC to PC is a task, as well as computation is a task. Similarly, we can divide the large tasks into a simplified tasks. Then parallel execution, we have to run each and every task that we have identified with separate time loop or parallel loop structures in LabVIEW. So we have to, while doing this, we have to ensure that tasks can communicate through queues to pass data safely between acquisition, processing, as well as data logging, as well as reporting. We have to ensure it. That real-time constraints, so we have to assign high priority data acquisition tasks to ensure timely data capturing, because the data capturing is the foremost task to which gives information to upcoming tasks. So we have to assign high priority to data acquisition. Then we have to set appropriate priorities for processing the data as well as logging tasks based on the criticality. Then deployment, so we have to configure the project to run on real-time targets like compact view, deploy and test the application to ensure it meets the real-time performance requirements. Thank you. Hope this video will give you more insights about multi-threading, real-time operating system, how to implement multi-threading as well as real-time operating system in LabVIEW. Also, we have discussed an example how we have to separate a tasks and how we can give the priority based on the tasks like that. Thank you.